as announced, the last talk, starting, well, why doesn't it want to shift? Starting with the image you've probably seen a couple of times already. So as part of the materials design box, starting on the left side with a structural and chemical atomic complexity, going to defect phase diagrams and going to material properties, which is the goal of this CRC, to establish this as one pathway for tailored future materials. And in this talk by me and Daniela, and me starting circling around three type of questions. So concerned with the last bit after the talks of Steffi and Tillmann and Jörg and Jochen. So how to link the defect phases with mechanisms and with properties, and how are the space of experiments, the chemical potential and engineering actually connected. And lastly, but not least, of course, the importance of defect phases also in corrosion. Starting with the experimental space, you heard this already in way more depth in the previous talks. So as a function of the chemical potential, it's now possible to investigate with high-resolution techniques and computational methods the structure and the chemistry of defects, resulting in the defect phase diagrams. And now it's the question, how do we get from the experimental space via the mu space, via the space of the chemical potential, to the engineering space? And the first step done by probing is to elucidate on the mechanisms of those defect phases. So here on the examples of dislocations, investigating determining the glide planes, for instance, here in this example, by micropillar compression, on the previous example, but also of a magnesium-based alloy. And when these mechanisms are activated, it's also possible to investigate the respective properties of these mechanisms. So here, staying with dislocation glide, it's possible, of course, to vary the orientation of these micropillars. By this, loading different planes of the crystal and measure the respective critically resolved shear stress. So the spots on this property diagram can get color in this case, so as a function of the critically resolved shear stress. And when there are these different mechanisms and their properties have been evaluated, they are of course in competition. So here in this, for deformation mechanism and for dislocation glide, the question is, of course, which slip systems are actually active. And here, being in the single crystal micropillar case, the lowest critically resolved shear stress would be relevant, and one can determine as a function of the chemical potential what is actually happening. Is it pyramidal slip? Is it basal slip? Or? So we have defect phase diagrams, we have the defect mechanisms and their properties, and we can plot these mechanism diagrams. That's just to highlight, of course, this was an example for dislocation glide. However, there are more defects and, of course, more corresponding defect phase diagrams for twinning, for phase boundaries, for surfaces, and also for corrosion, which you'll hear about a bit more later. And now the question would be, well, as before mentioned, this was for the single crystalline case. In order to come from or move from the experimental space finally to the engineering space, where bulk, at least bulk materials more than a single crystals are relevant, we want to, of course, move on with the aim going towards the microstructure bulk property relationships. And how to do that? What we want to arrive at the end, while still being in the mu space, in the space of the chemical potential, we don't want to only know, okay, it's good to know what slip system is active, but also, is the material, for instance, brittle or is it ductile? And here, for instance, of course, general metal physics will help to know, okay, we have many slip systems, or we might have less. And of course, we're also able to transfer the single crystalline information which we have to actually polycrystalline materials. Here, of course, mainly in the project C1 with Franz Rothers and Steffi Zander for implementing this data and simulating how actually the material behaves when it's in a polycrystal, which of course might have texture, which might have effects of different grain sizes, etc. So at the end, when we do this, and we validate this also by bulk probing, we'll be able to draw diagrams where we can actually say here with the material is behaving brittle, here for instance it's behaving ductile. Now, what's also useful in these cases is to going backwards. When we do actual experimental probing, we will observe most definitely abrupt changes in properties. So for instance, imagining a tensile test, you're looking at ductility, and once you vary the composition, hence also the chemical potential, there will be the case here marked by these red crosses on the right side, that we see something where the ductility suddenly changes, either jumps up or jumps down, which of course highlights that something is going on in the defect phase diagram, the interaction between the chemistry and the crystallography. For this purpose, we want to employ combinatorial studies as well as real, so to say, larger scale bulk materials. So in the project of Jochen Schneider, B2, it's screening by thin films, and in a slightly less proliferation of compositions in actually my project C4, actually doing combinatorial studies, so investigating lots of materials with different compositions, hence chemical potentials. And then finally, interesting compositions which have been narrowed down, scale them up, produce them on a larger scale, distribute them to the projects to investigate actually the underlying structural and chemical atomic complexity, because of course these investigations take quite a lot of effort to do with sample preparations and analysis and etc. So here, hopefully, combinatorial studies plus upscaling will help us identify very interesting, relevant changes more rapidly, and hence also make the construction of these defect phase diagrams more efficient. Yeah, now, so to say, as the last step in this workflow from the defect phase diagrams on the right, the overall goal at the end also encompasses hopefully being able to leave the space of the chemical potential as a translator, so to say, a coordinate system, where actually looking at the material behavior which has been described as brittle or ductile into something excuse me, known as SFB maps or Pourbaix diagrams, etc. So actually diagrams as they are utilized every day by materials engineers, where one could readily, hopefully, look up and say, like, okay, for instance, what type of strength can I expect as a function of temperature, or what type of stiffness, or what value of stiffness can I expect as a function of the chemical composition. At the same time, also relevant for the translation to engineering space is, of course, the information coming out of the synthesis project, mainly, of course, B2 and C4, with S working together with both. When we have desired defect phases and desired microstructure morphologies, for example, all that knowledge which we've studied there will help us to identify and describe these causalities. So not only knowing what material behavior is favorable or unfavorable, but at the same time also knowing how to get there, how to actually create these materials, at least the framework, hopefully to pass over to really volume material production. What, for instance, what solidification rate is necessary in order to get a specific mechanical or chemical behavior of a material. Putting all this back together in one complicated diagram, which I hope I could talk you through it a bit, from the defect phase diagrams via probing to the defect mechanisms and properties. The competition between these properties allows to draw mechanism diagrams and transferring this data via crystal plasticity and bulk tests into real bulk diagrams of the properties and the behavior. And later on translating this into engineering type diagrams of the type of Ashby and Pourbaix. Yeah, this also due to the time limitations back then from the evaluation talks. This was, of course, just one example. It's in the framework of the CSC, of course, more complex. It's not only one type of defect, as alluded to earlier. There are multiple defects of increasing dimensionality. Here said, okay, dislocations to up to 3D skeletons in composite materials. We have, of course, materials ranging from solid solution to composites, e.e. solid solution containing intermetallic phases. So a lot to do in many fields of work. However, one thing which we thought back then, and I believe still think, was very viable, I've talked now a lot of mechanical properties. However, these defect phases determine not only the mechanical behavior, but just as well the corrosion properties, which of course, at least in the engineering world, might be just not as or even more important as the actual mechanical behavior. And with this, I would hand over to Daniela, taking over the second part of the talk.
So thanks, Hauke, again for introducing the need of defect phase diagrams to determine mechanical properties. And now it's my pleasure to introduce the needs of the implementation of corrosion properties within the CRC. And as already was described in the presentations before the last weeks, we see that there's not only a lot to do in material science and mechanical engineering, but also in corrosion science and engineering. And we believe strongly that the major link between mechanical and corrosion properties is determined by defect phase diagrams. So therefore, we want to follow within the CSC also the multi-dimensional approach for corrosion science. So typically in corrosion science, we are focusing in research on the area between the mu space and the engineering space by considering only the bike properties. And if we, for example, focus on the development, which is shown here, of high-strength aluminum alloys, an increase in hardness and strength will be obtained by different heat treatments, such as solution under-aging and peak aging treatments. And this is typically associated to microstructure-depending hardening mechanisms. So, however, if we consider not only the mechanical properties, but also the corrosion properties for those materials, we clearly see a tremendous effect of the microstructure evolution on the corrosion properties. So, for example, here you clearly observe on this slide a mechanism change from pitting to intergranular corrosion with increasing annealing time. And the reason could be related to the formation of a copper-enriched grain boundary and a solution-depleted zone, and therefore strongly depends on the existence of defect phases. So, however, this observation are most of the time only qualitatively, and there's a strong need to fill the gap between the experimental and the engineering space. And so what would you say is missing to fulfill this need in corrosion science and engineering? And if I or we would have to answer this question, we would say, on one hand, the understanding of the influence of defect phases on corrosion reactions and mechanisms of single phases, surfaces, and composites in specific environments is missing, as well as the identification of mutual effects of defect phases on corrosion and mechanical properties, and in addition, the use and development of local measurement methods. So therefore, we expect to close the gap between the experimental and the engineering space by focusing on the development of defect phase diagrams and mechanism diagrams, by understanding localized corrosion mechanism and its properties, and this knowledge then will be transferred to so-called defect phase Pourbaix diagrams. So how will we do this? So we will do this by using sophisticated methods and focusing to relevant scientific hypotheses. So as you can see on this slide, all areas who are associated to bridge the gap between the experimental space to the engineering space are reflected by corrosion-related projects covering multi-dimensional approaches of the CRC grant. So within these projects, the transfer from the experiments towards the simulation and backwards will be guaranteed by the use of localized high-resolution methods, as well as by advanced simulation approaches. So besides that, our overall scientific corrosion hypothesis in regard to defect diagrams is that corrosion relevant defect phases such as interfaces and dislocations can be experimentally identified, predicted by simulation, and associated with a specific chemical potential. So defect phases determine corrosion mechanisms and properties. Identified transitions in the phase diagrams are linked to mechanism changes in the mechanism property diagrams. And as you heard last time, abrupt changes in the bulk properties are used for the concept of guided probing. And finally, the development of defect phase Pourbaix diagrams based on defect phases represents an innovative approach for corrosion science and technology. So to successfully address the corrosion-driven hypothesis, we need 4 major requirements. On one hand, the identification of the original surface conditions. Second, localized mechanistic understanding. Third, combinatorial design and guided probing. And fourth, simulation of defect phase and Pourbaix diagrams. And I will address in the following these requirements in more detail. So the first requirement, to identify the original surface condition, is necessary because the surface condition influences typically also the corrosion mechanism. And therefore, we are especially interested in the investigation of the interface between the metal and the original oxide layer. And as you can see here, we have the ability to identify the structure and chemistry, for example, by high-resolution STEM and yields measurements. And here, an interface between pure aluminum and the metal oxide of an oxidized surface prepared by cross-sectional FIP shows nicely the formation of a defect phase, as an example. So the second requirement is to understand localized corrosion mechanism and to identify the related properties. And if you consider the example from the beginning of my talk on the intergranular corrosion of high-strength aluminum alloys, we identified 2 defect phases, such as the grain boundary and the phase boundary defect phase, given by the kappa-enriched grain boundary and the solution-depleted zone. Combining this with the local corrosion properties, this will allow us not only to evaluate the corrosion mechanism qualitatively, but also quantitatively by inserting both information in the mechanism diagram. And therefore, for example, defect phases with a positive corrosion potential acting stable, such as kappa-enriched grain boundaries, compared to active defect phases with a lower corrosion potential, can be directly related to the chemical potential. The third requirement is based on the hypothesis that property changes are caused by mechanism changes. And if we, for example, consider the integral and macroscopic corrosion behavior of the magnesium alloy AZ91D, processed by different processes, here you can see it as Tixomolding and high pressure die casting processes, we clearly see in the current density potential diagram, in the first diagram, a significant difference in the corrosion potential. And this abrupt change of the corrosion potential indicates a corrosion mechanism change and is expected to support our guided probing approach. In addition, it indicates that the corrosion mechanism is based on the formation of microgalvanic elements between the more noble intermetallic phase and the magnesium phase, dependent on the phase fraction. However, this is an old and conventional idea of dealing with microgalvanic corrosion mechanism. We want to do this here differently. We would like to look more carefully to the corrosion mechanism, and if we think about the corrosion mechanism of this example, we clearly see an influence of defect phases at the phase boundary here, and this we would like to investigate for the alloy system of the CRC. And this example seems to us to prove also the need for a better localized mechanistic understanding. So the last requirement to enable the transfer from the experimental to the engineering space for corrosion is given by the simulation approach of corrosion-relevant defect phases and defect phase Pourbaix diagrams, and that's quite challenging here. But with this project, we have a good example here also given already, that the simulation, for example, of a zinc oxide surface in contact with various pH dependent aqueous electrolytes gives us more information on one hand on surface phase diagrams, but also allows us to develop a defect phase surface Pourbaix diagram. And as you can see here, each of the differently colored regions within the defect surface phase diagram, the left-hand side diagram, shows the chemical potential conditions for which a distinct surface state is stable. So further, a change of the surface reconstruction, here shown in the middle, was observed dependent on the chemical potential. On one hand, flat surfaces with absorbed species were identified, and on the other hand, a triangular reconstruction indicates a corrosion mechanism change. We also can show by this example on the right-hand side that we have the tools for a successful construction of defect phase Pourbaix diagrams coming from a defect phase diagram. So finally, we hope with this last slide that we showed you the importance and need of the concept of defect phase diagrams, which allows us to link between the experimental space and the engineering space by considering defect phases, local mechanisms, and mechanical as well as corrosion properties. And this is expected to result in a high degree of innovation by making a materials design toolbox available to tailor new materials. And therefore, I would like to thank you in the name of Hauke and me for your attention. And of course, we will be happy to answer your questions.